Okay, this is lesson 10. It's one of two parts. The first part, I will go through the actual required practical. So these are the kind of things you may come up in an exam question. The second part of the lesson will be all to do with the equations that we will go over. So you've done this force extension practical quite a few times. First time is in year 7 in the space module. You do it again in year 9. We sometimes call it Hooke's law, named after Robert Hooke, who figured it out. So Hooke's law. And it's just a nice little piece of linear experimentation. So it starts with the idea of a spring. When you don't have any force applied to a spring, you have what's called a natural length. And what we're interested in is what happens to this spring if we attach weights to it. So hopefully by now you're having a oh yeah moment, because you've definitely done this a few times. And we're looking at what happens if we change the amount of force to, not Fe, F-O-R, the amount of force, so we add weights to it, for example 1 Newton, 2 Newtons, etc. And we measure the extension of the spring. Now the bit people all get mixed up is this word extension. So extension is how much larger has it got from its natural length. So if I mark here the natural length, with no force attached, then we measure the new length, so the entirety of the new length here. All we're doing is taking the natural length away from the total, and that will give us the extension. So if I write it out like that, so we can write it algebraically like this. Extension, which is in red, extension is equal to the natural length, no it's not, the total length. I'm being distracted by my chihuahua going crazy over his food. By the total length minus, that T looks like a H, minus the natural length. There we go, got it in the end. Natural length. Now because it's a required practical, the actual memorizing the practical, not that hard. They usually show you a picture. What they're actually getting at is these key ideas. Now if you remember all the way back to lesson 6, trolley dash, where we investigated Newton's second law, again we were looking at a practical, but it was all about the key scientific words, about how we do it. And this is the same. So hopefully if you did that one, this second one will be a lot easier. So let's go back to it and have a look. So first thing is resolution of the equipment. Now usually what we do here is we attach, and I'm just going to wipe out the total length so I can attach a ruler. And we line the ruler up, put my spring back in. We attach a ruler along here, and what we're doing is we're looking for the measurement on the ruler. It's not quite straight. Get the idea. Now, the resolution of the ruler, if we were drawing a ruler, usually 1 centimetre 2, but we would have millimetre markings. So the resolution of this experiment is the length is measured in, it's not equal to, but it's in millimetres. The force, trickier this one, these come in 1 Newton, 100 gram masses. Now obviously if they get hit and they lose a little bit, but we're supposed to be there accurate to at least 0.01 of a Newton. Okay, so when you put one on, you can be fairly confident it's 1 Newton. Quite how far that goes, I do not know. Next, we'll look later at the range for our results and the uncertainty that those generate, because they come together. But now we go on to errors. Now, errors, there are 3 types if you remember. The first one is something we cannot avoid, and it's called the random error. And if you remember, the solution to the random error is to do this experiment 3 times, then find the mean. So that's what we would do to try to eliminate random error of this experiment. Do it 3 times, find the mean. Hopefully, it eliminates any random errors. Next, systematic errors are errors where you do the same thing wrong, but every time. They're quite easy to spot because usually everybody else's graph goes through 0 and your graph won't because you'll be off, either above or below, like so. And they're easy to spot and easy to fix because you just subtract the amount of systematic error. So that could be something like, trying to think of one, I can't at the moment, because I want to get onto 0 in error, because this one is a classic for zeroing. And the zeroing error comes from the fact that some people do not subtract the natural length, the total length, and then subtract the natural length. So what they end up with is this top line here, where 0 isn't 0. They should have no extension with no weight on it, but they do. They have an extension, and it will be here. Say the spring was naturally 2.5 centimeters long, and they will be constantly 2.5 centimeters off where they should be. It happens every lesson without fail. And so you have to go around and you have to subtract 2.5, the natural length, off all of your total lengths here. So this one's a really good example, and if I was an examiner, this is the one I would use to test that on, because you haven't zeroed it, you've carried that natural length over. So that's that one. Now, accuracy. Again, there's a really nice bit. I've seen it come up a few times in the exams. How do we get close to, if you remember, the accurate is the true value. We want to hit the jackpot here. So I really want to measure this length here. Somewhere here is the true value. So what we do in this practical is we recommend adding a pointer, a stick or a pin that has a very small surface area that can very accurately point to it. And that will allow you to measure and get very close to the true value. The other thing is, when you let go of this, the spring stretches up and down, and you must wait for it to stop moving before you take your reading. So make sure you write these notes down. If I don't write it, but I say it, you still got to write it. Okay, so those are the 2 ways we get accurate. 2 ways. So rewind it if you missed that, write it down. And the last one is precision. Precision is the idea that each result is as close to the previous result when you do it 3 times. So if you had, 2 newtons there, let me just get rid of that. If you had 2 newtons and you were measuring the extension 3 times, and you got, 4.6, 4.5, 4.7, then your precision is pretty high. All 3 numbers are very close to each other. Whilst I've written that, that takes me over back to range. And if you remember, range is biggest, take smallest. And in my case, I was crafty, I did it on purpose. I left 0.2 from the smallest and the biggest. So in this case, 0.2 between them, centimetres in this case, because this is extension. And the final one is the uncertainty. And if you remember, the uncertainty is range over 2. Range over 2. So in this case, the uncertainty would be 0.2 over 2, which is plus minus 0.1. And that really sums this one up. My advice is use the PDF that I've attached to copy it, make better notes than I've written here. But bear in mind, it's not all about learning the practical per se, it's all about applying these key ideas. In the second lesson, we'll look at the equations and how to apply them, and the common mistakes people make. As always, snap a photograph of your notes, post it online. I'm seeing some really good work. I've got to sit and put a load of merits on for you guys. It's never too late to catch up, or even if you want to join us halfway through and just start on lesson 10 if you've missed the rest. That's no bad thing. I'd rather you do a little than nothing. All right, I look forward to seeing all your work. Take care. Bye.